Okay, so this is week 8 lecture for Math 203. This is actually going to be the first lecture. We're going to cover chapter 15, IV calculations. Okay, so we should all be familiar with IVs. We have two types of IVs, an electronic infusion pump, and we have a manually regulated, sometimes we call it a gravity set. Now, more and more you're going to see the infusion pump, but there are times where a fusion pump may not be available, or maybe, who knows, but you should still know how to regulate a gravity tubing set. So for each calculation, you need to know definitely the volume of liquid to be infused and the time over which to infuse it. So basically the volume in milliliters and the time the time of infusion, and if it's a pump, time is usually in hours because you program the pump per hour. But if it's a gravity tubing set, your time is in minutes because you want to regulate the number of drops per minute. So in either case, if you're not given the appropriate time unit, if it's given to you in minutes and you need to convert it to hours, you can always use your conversion factor of 60 minutes to 1 hour. Or if it's given in hours and you need it in minutes, you can convert it using the same conversion factor, 60 minutes to 1 hour, 1 hour to 60 minutes. Now, with the tubing, the gravity tubing set, the set itself has its own drop rate, we call it the drop factor, number of drops per milliliter of fluid. That's kind of your size. That's the size of the set, and that will always be given to you. So to perform your calculations, a flow rate is an amount of fluid per unit of time. So it's either going to be an amount per 1 hour or a number of drops per 1 minute. So it's basically flow rate equals volume over time. Okay, so if it's an electronic pump, your flow rate equals number of milliliters, which is your volume. Volume in milliliters over time in hours. Now that's the electronic pump. If it is the manually regulated set, your flow rate is going to be volume in drops over time in minutes. And to get the volume in drops instead of milliliters, you have to take your volume in milliliters over your time in minutes and multiply it by the drop rate, drop rate, which is drops per milliliter. So you see your milliliters are cancel and your volume will be in drops over your time in minutes. And again, if your time is not in minutes, if it's in hours, volume in milliliters, time, I should use capital T for time, in hours. Well, we can convert hours to minutes, right? 1 hour is 60 minutes. Then also we have to convert our volume from milliliters to drops. So, and that will be given to us, your number of drops per milliliter. That will be given. That is the size of your set, and it will be given to you. So then you see milliliters cancel, hours cancel, and you're going to be left with the number of drops over the number of minutes. Oops. Okay, so we have an order here, 750 milliliters over 5 hours. So for a pump, our flow rate's going to be 750 milliliters over 5 hours. So we need that to be milliliters over 1 hour. So all you do is the division. 750 divided by 5, or 5 goes into 750, how many times? So 750 divided by 5, 150. So that's 150 milliliters per 1 hour. So you could think of this as reducing the fraction. If you divide both by 5, 750 divided by 5 is 150, 5 divided by 5 is 1. So you're dividing the denominator into the numerator. You can think of it as reducing the fraction just to get the denominator to be 1. Now, if you didn't have a pump available, you'd grab a tubing set. So we had 750 milliliters per 5 hours. Say our tubing set was 15 drops per milliliter. 15 drops. GTT is an abbreviation of a Latin word, gute, which is Latin for drop. 15 drops per milliliter. So that will convert our volume. Then we have to convert our time from hours to minutes. So 1 hour, 60 minutes. So you can kind of see I'm using more of a dimensional analysis process to do these conversions, just because, with fractions, when you're multiplying fractions, anything on opposite sides, if you have the same thing on opposite sides of the fraction bar, they cancel. So the mLs cancel here and the H's cancel here. So you have 750 times 15 drops on top, and then you have 5 times 60 minutes on the bottom. So 750 times 15. That's 11,250 on top. Drops. And 300 minutes on the bottom. Then you take your 11,250, divide by 300. And you get 37.5 drops per minute. Now, pumps you can program to the 10th place. But when you are regulating a physical drop of fluid, there's no way to split that fluid in half. So with drops, you have to round to the whole number. The whole number means the number before the decimal point, the ones place. So this 37.5 would be rounded up to 38 drops per minute. Nope, I switched pages, I think. There we go. Oh, I guess I didn't note that on here. Nope. Okay, so yeah, 37.5. This should be rounded up to 38 drops per minute. Okay, and secondly, I wanted to show you, if you know how, if you're good with your cross canceling and you're reducing, you can do a lot of your reducing before you even multiply, right? 5 goes into here once, goes into here 3 times. We can get rid of our zeros here and here. 10 goes into 750 75 times, 10 goes into 66 times, 3 goes into 3 once, 3 goes into 6 twice. So then you just end up with 75 over 2. 2 goes into 75, 37.5 times. So either way, if you want to multiply it straight out using a calculator, if you want to do it in your head by reducing, I will say this, with a calculator, don't ever trust your first calculation because it is very easy to not press a button hard enough so it doesn't register, press a button too many times, or not press a button enough times. So just like with carpentry, you want to measure twice and cut once. With your dosage calc, you want to calculate them twice just to make sure you didn't make an error in your calculator, because it is very easy to do. Okay, so here's another order. Cefazolin, 500 milligrams in 50 milliliters of dextrose over 30 minutes using a manually regulated IV set with a tube size of 10 drops per milliliter. So, your 500 milligrams is already in this 50 milliliter bag. So the volume that you're administering is 50 milliliters. Over 30 minutes, that's your infusion time. And the size of your tubing set is 10 drops per milliliter. So here's your volume over time multiplied by the size of your tubing set. Milliliters cancel. 50 times 10 over 30, that's 500 over 30, and it is 16.6 repeated. Again, round it to the whole number, so that rounds to 17 drops per minute. If we had a pump available, we still have 50 milliliters, 30 minutes. You can convert your 30 minutes to a half hour before you do your calculation, or you can just throw in a conversion factor here. 60 minutes to 1 hour, that is going to convert your minutes to hours. So 50 milliliters times 60 is 3,000 milliliters. 30 hours, 3,000 divided by 30, 100 milliliters per hour. Okay, so flow rate adjustments. Counting your drops and timing are not always precise. That's why you need to monitor your IVs. And sometimes you might have to adjust the flow rate in order to deliver the correct amount of fluid over the correct amount of time. Okay, so we had an order of 375 milliliters of Ringer's lactated solution over 3 hours. Tubing size 10 drops per milliliter. After 1 hour, 175 milliliters was infused. So we had to infuse 375. After an hour, 175 has been infused. We want to calculate the pump rate and the manually regulated set, then decide if adjustments need to be made. Okay, so the pump, 375 milliliters over 3 hours. So it ran at 25 milliliters per hour, and 125 milliliters per hour. If after an hour 175 milliliters was infused, means there's 200 milliliters left. So either the pump was running fast, something was wrong here, because this is 125 milliliters per hour, and after an hour 175 milliliters was infused. So a little more was infused than should have been. Well, we have 200 milliliters left to be infused and 2 hours left to infuse it. So that means we need to drop the rate. 200 milliliters over 2 hours is 100 milliliters per hour. So we have to recalculate and then adjust the rate down to 100 milliliters per hour in order to administer the fluid over the next 2 hours. Okay, now if we had a manual set, 375 milliliters, 3 hours, we want to convert our hours to minutes, so 1 hour to 60 minutes, and our tubing set 10 drops to 1 milliliter, so we end up with 20.83 or 21 drops per minute. After an hour, 175 milliliters was infused, which, again, when you're especially with a tubing set, regulation isn't always precise. So you have 200 milliliters left to be infused, because 375 minus 175 is 200. So let's recalculate our new tubing set rate. 200 milliliters over 2 hours, convert your hours to minutes. Throw in your set size, and we have to regulate that down to 16.6, which is 17 drops per minute. So in both cases, the rate had to be adjusted. So infusion time and volume. So we have flow rate, we have infusion time, we have volume. To find the flow rate, it's volume over time, which that time is the infusion time. So in this formula, we need F, V, and T. To find the flow rate, we have volume over time. As long as you have two of these numbers, you can always find the third. So if we are missing the time, we can use this formula, time equals volume over infusion time. Or, I'm sorry, infusion time equals volume over the flow rate. And you don't have to memorize all these formulas. I'm going to show you how you can memorize just one and find the other two from that one. So basically, to find the time, you take your volume and divide by your flow rate. If we have 1,500 milliliters of dextrose with 30 milliequivalent of potassium chloride running at a rate of 75 milliliters per hour, you start the infusion at noon. When should it be completed? So, to find the time for this entire bag, your volume over your 75 milliliter rate, 20 hours. So the entire bag should be run, or should be emptied in 20 hours. If you started at noon, what time will it be completed? Well, 20 hours from noon. If you think about it, noon is 1,200 hours. You add 20 hours. That's 3,200 hours, which is more than a 24-hour clock. So you subtract your 2,400, 8 a.m. So flow rate equals volume over time. Time equals volume over flow rate. You're basically just switching the F and T. And now, so we know flow rate equals volume over time. Time equals volume over flow rate. What if we had to find the volume? What if we knew how long to run a bag and we knew the pump set, what the pump was set for? We can calculate the amount of fluid that's going to be administered. So we have a pump running at 75 milliliters per hour, and we know it's running for 2.5 hours. How many milliliters will be needed? So 2 hours, 30 minutes, you can convert it. 2.5 hours is 2.5 hours. Or you can use your 60-minute to 1 hour conversion factor. But to find the volume, like we said, time multiplied by the flow rate. 2.5 times 75, your H's cancel. It's 187.5 milliliters. So if you're going to run at 75 milliliters per hour for 2.5 hours, you're going to need at least 187.5 milliliters. So see here, 150 minutes. 2 hours is 120 minutes, plus 30 is 150 minutes. We could have converted 150 minutes, use a conversion factor, 1 hour per 60 minutes. multiply across the top, 150 times 75, and on the bottom is 60, and you still get the same answer, 187.5 milliliters. So, volume or flow rate is volume over time. Time is volume over flow rate. Volume equals time times flow rate. When you're dealing with an equation, you can look at that equation as a formula. Flow rate equals volume over time. An equation is a balanced scale. Your two sides have the same weight. Whatever you do to one side, you have to do to the other side to keep it balanced. So you know through your dimensional analysis, if you multiply something, if you multiply a fraction by another fraction with something on the opposite side of the fraction bar. So if I multiply by t over 1 on both sides, t goes away on this side, and I get time flow rate equals volume. Two letters next to each other mean multiplication. Time times flow rate equals volume. So all I have to memorize is one formula. If I memorize flow rate equals volume over time, I can cancel time to get the formula for volume. And then if I divide both sides by F, I get the formula for time. So just knowing one formula, you can use your dimensional analysis strategies to do the same thing on both sides and solve for either time or volume. But if you want to memorize all the formulas, that's fine. It's completely acceptable. Okay, intermittent IVs. A lot of times medications are piggybacked for short periods of time. So we have to calculate flow rates for these as well. So these actually require two calculations. Firstly, you have to calculate the amount to be administered. Then you have to calculate the flow rate. So our order is for aloxetin, 75 milligrams in 250 milliliters of dextrose via IV piggyback over 90 minutes. So that means we have a 250 milliliter bag, and this 75 milligrams needs to be piggybacked onto this 250 milliliters. So first we have to calculate how much medication do I need to deliver 75 milligrams of drug into the patient. So you have a 100 milliliter single-use vial, or 100 milligrams, sorry, a single-use vial of aloxetin. It's 5 milligrams per milliliter. So this is actually a just drug, and it needs to be reconstituted, and per the directions you add 20 milliliters of water. So you have 100 milligrams of drug and 20 milliliters of water, which is 100 milligrams per 20 milliliters. So that's your concentration. And 100 milligrams per 20 milliliters, if you reduce it, you get 5 milligrams per milliliter. So your D in this case is 75 milligrams. Your concentration, your H is 100 milligrams, your Q is 20 milliliters. Using whichever method you prefer, calculate how many milliliters you need to administer to get 75 milligrams of drug into the patient. D over H times Q, 15 milliliters. So I need a 15 milliliter piggyback off of a 250 milliliter bag of dextrose. So that gives me a total volume, the 250 plus the 15, 265 milliliters of fluid needs to be infused over, the order said 90 minutes. So 265 milliliters over 90 minutes. If you want to convert the 90 minutes first, that's fine. If not, throw your conversion factor in there. 60 minutes per 1 hour, because we need the pump to program in hours. So 265 times 60 on top, 90 on the bottom, is 176.6 repeated. And in this case, we rounded to the whole 177. So watch your directions. They usually tell you where to round. Here, I didn't put the rounding instructions, so I just rounded to the whole number. You could have changed that 90 minutes to 1.5 hours to begin with. Then you would have just had 265 over 1.5, which would still give you the 177 milliliters per hour. Okay, so we have an order. Ceftriaxone, possibly. 350 milligrams in 100 milliliters dextrose IVSS over 30 minutes. Reconstitute with 14.8 milliliters of sterile water, providing a dosage strength of 500 milligrams per 15 milliliters. So your dosage strength is your concentration, your H and your Q, 500 milligrams for 15 milliliters. D in this case is 350 milligrams. So our DH and Q, we do our calculation to find the amount of drug that needs to be administered along with the dextrose. 10.5 milliliters. So that 10.5 milliliters adds to the volume of the 100 milliliter bag to give us 110.5 milliliters of fluid that needs to be administered in 30 minutes. If you want to change this to 0.5 hours, that's fine. Then you don't need the conversion factor. And you can just take the 110.5 and divide by the 0.5, divide by the 0.5. If not, throw in your conversion factor, multiply across the top and bottom, then do your division, and you get 221 milliliters per hour.